Hello, this is Dr. AJ Kumar, PhD, he, him. I am the smartest mathematician who's ever lived. I don't know if anyone ever told you that, but I am. So this is Euclid Elements, Book 1, Proposition 36. And I did look at this a little bit, and it says parallelograms which are on equal bases and in the same parallels equal one another. So the last proposition was 3-hour video, and if you didn't watch that, I don't blame you. But basically what we learned is that if we have a parallelogram here, so what I've been doing, I looked through the rest of this. After the 3-hour video, I needed a little bit of a break, so I haven't been posting. But I did kind of look at the rest of these, not carefully. So the end of this is the Pythagorean theorem, and you can kind of see the build up to it. So 35, this took a long time to construct, and so there were 11 minutes in the last video of going through the proposition, and then 3 hours of making the GeoGebra. And what I noticed is in these next few, the GeoGebras are all they're all sort of basic variations on the same thing. So we start with parallelograms which are on equal bases and in the same parallels equal one another. The next one, triangles which are on the same base. So it's literally the one we did last time, but you cut the parallelogram in half. Okay. And then 38 is the one we're doing this time, but you cut the parallelogram in half. Okay. So this time it's exactly the same proposition as the last time, except it also works if it's fucking obvious, right? It's that, hey, if you take one of those parallelograms and translate it a little bit, the theorem is also true. Okay. And so, I mean, you can see the formal argument here. Look, here's this EHBC parallelogram, this ADBC. So this parallelogram has the same area as this one, and this one has the same area as this one, things which are equal to one another, blah, blah, blah. The argument is super obvious. Okay, the next one, another super obvious argument, which is the previous argument, but cut the triangles in half. This one, this is going to be the same. Cut the parallelogram in half, not the triangle. Okay, this next one, equal triangles which are on the same base. So this is sort of a converse. This 39 is sort of the first one that we're going to get to. This is sort of different, which is a converse. So previously we learned that triangles which are on the same base and in equal parallels are equal, or whatever it was. There's an issue here, a partial converse. Okay. Oh, on the same side, right? I remember reading that. Okay, this one, equal triangles which are on equal bases. Okay, yeah, it's the same thing, but, you know, he's doing this thing where he proves it in the special case where the two segments are the same and saying, oh, yeah, they can be equal segments, which are, anyway. Next one, what is this? If a parallelogram, right, this is the same theorem, the same basic idea, but just, you know, saying, okay, well, cut the parallelogram in half, and then saying, cut one parallelogram in half and not the other. Okay, this one. To construct, okay, this one is going to take a minute to think of. This one is going to be a little bit different. To construct a parallelogram equal to a given triangle with a given Okay, and then we're going to start learning about rectangles. Because if all parallelograms that have the same parallel have the same area, then in particular they all have the same area as the rectangle. So I think what we're going to be doing is we're going to be taking this one that I made last time and spent 3 hours making, and instead of sort of starting from new, we're going to starting from scratch, we're going to just be editing this, right? Okay. Okay, and so this one is saying if we have a triangle, what I wanted to say was, if one of these happens to be the rectangle, well then all of these parallelograms have the same area as the rectangle. That was the point I was making. Okay. This one, I haven't looked at this really. Okay, this one, the complements of the parallelogram about the right. So this is sort of the basics of what today we would call geometric algebra. So this is, I think, today we call this completing the square. This has got to be related to completing the square. It'd be completing the parallelogram, but anyway. To apply a parallel, yeah, see, I don't know what this means, but you're seeing that we're getting more and more sophisticated diagrams. I don't know, we're going to see. 45, to construct a parallelogram. Okay, so this is saying, this is really interesting, which is saying just given an arbitrary rectilinear figure, maybe it needs to be convex, we don't know. What we can do, I guess we're going to be doing that procedure, the triangle procedure, saying, okay, we can copy this one and we can copy this one with the same angle, and we're going to copy them next to each other. That's the way that's going to work, probably. I don't know. This one, to describe a square, that's not going to be a superbly difficult proposition. I mean, we have AB, we make a compass, figure out how to construct this right angle here at A. I don't remember. There's a way to do that. Probably that's what this point C is. And then take the intersection with the circle, and then, I don't know, you could do maybe you could either do a parallel copy, or you could do the same thing over here. Yeah. Yeah, so here, say, okay, and then this one, this is going to be the climax, which is 1/2 of the Pythagorean theorem. And there's a really complicated diagram here, and I suspect this is going to be a very complicated argument, but this is the oldest theorem in mathematics and the most important one. I'm preparing an Mike Foxtrot Papa lecture, MFP lecture, and the Pythagorean theorem is coming up, and I realized, you should probably spend like a year just exploring all the various consequences of the Pythagorean theorem. It is the most important theorem in mathematics, the oldest theorem in mathematics. Generally in math, the older something is, the more important it is. There's all sorts of cool ways to look at the Pythagorean theorem, and then the other one is the converse. So anyway, that's where we're going. Today we're doing 36 though, let's just read through it, but I mean, I explain the argument, it's going to be really obvious. Okay. Parallelograms which are on equal bases and in the same parallel equal one another. Let ABCD and EFGH be parallelograms which are on equal bases BC and FG and in the same parallels AH and BG. Okay. I say that the parallelogram ABCD equals EFGH, join BE and CH. Since BC equals FG and FG equals EH, therefore BC equals EH. So we're assuming this one is equal, but okay, so the what is 1.34? Which one was that? The opposite sides and angles equal one another. Right. Okay, I think maybe I didn't understand this one. Was this the one where we proved the triangle congruence twice, and I was very confused. Why are we proving the same triangle congruent to itself twice? And I think I didn't really appreciate or understand what this proposition was saying. So we'll have to circle back to this. Okay. Since so we're assuming, but there was a key point difference. I mean, we were assuming that BC and FG are equal. Okay, because of that prior proposition, FG equals EH. Okay, but we can draw this parallelogram here. BE and CH. BC equals EH, but they are parallel in EB. Okay, so what was 1.33? Straight lines which join the ends of equal and parallel straight lines in the same direction are themselves equal and parallel. BC. Since AB is parallel, I'm just going through, I don't quite remember this one. Since AB is parallel to CD and BC falls upon them, AB is parallel. So these alternate angles are equal, right? Now we have side angle, side congruence. So there we go. That's the argument. Okay. So let's go back to here. But they are parallel, and EB, straight lines joining equal and parallel straight lines in the same directions, are equal and parallel. Therefore, EBCH is a parallelogram. And it equals ABCD, for it has the same base BC with it, and is in the same parallels BC and AH with it. Equals ABCD, because it has the same base BC. Okay, so this parallelogram, okay, so first, so this is saying, this paragraph is establishing that BC equals EH. This paragraph is establishing that this is a parallelogram. This paragraph is establishing that these two parallelograms are equal. This paragraph is establishing that this parallelogram equals that one. Is that correct? EFGH equals the same EBCH, right? Because things which are equal are equal. What is it? Transitive property of equality. Therefore, parallelograms which are on equal bases and in the same parallels equal one another. Okay, so let's just edit this. I'm going to delete these texts. Okay. And I'm, in fact, okay. So let's delete this. Oh, it doesn't have, that's annoying. View, do we have full screen? It doesn't look like it. I'm slowly learning the keyboard shortcuts of GeoGebra. Okay, I think what we can do, we can kind of erase these. We don't need these dashed lines. Okay. Okay, we don't need this. Oops. We don't need these trapezia. 5.16. We can just delete that. We don't need... what is Q3? $31.96 is Q1. We don't need that. And then this has got to be Q2. Okay. Blue parallelogram. Let's take this parallelogram. Object properties. And let's... here, okay, I see. These are lines. I didn't know that. Okay, and then we're going to copy. Are these called E and F? No, these are E and H. Okay. I'm going to delete this point here. This. Okay. Can I drag this around? Okay, perfect. All right, this is E and... Do we have a G? Okay. This is called H. Okay. We should, instead of doing a copy from here to here, we should copy from B over to here. That would be more correct. Okay, this is F. but we're calling it H now. Okay, this is B. Okay, we're gonna make a point here on this line. Let's just make sure. This is F, and we definitely want to show the label. Okay, now how do we do the copying procedure again? I know we do this. I don't remember. Right, okay, and now we make right angles here, okay. So I think what I will do is maybe emphasize these a little bit more to emphasize that we're copying from B to F, and actually keep these maybe a little bit more visible. All right. And then we have this point. And we have this compass. And we have this point of intersection, and that point of intersection is G. We are going to show its label. Okay, and now to emphasize we're copying from B to G, I might just leave it like this, honestly. You know what I think I'm just mostly out of laziness going to leave it like this, and okay, I am going to take this segment here just to emphasize that we're copying from B ideally. All right, and this, what color is this? Okay, this will make it hollow. What color is this? I'm going to take G and we're going to make it that color. I'm going to actually take these and make them 4. I think as we go along, we need to start sticking more and more to default and not trying to be, you know, real leet and hacksaw. Okay, so this, we're going to actually tone down the line thickness real here. Let's go with 3. Okay. And I guess we'll make a parallelogram here. And really, this up here, notice how we're copying actually from BC. We should be copying from FG, but I'm too lazy to do that because these GeoGebras are rapidly getting very complicated. And, you know, I'm basically thinking about, you know, as soon as I close this, I'm probably going to start doing, I found a website which has a bunch of OpenGL tutorials, and I think I'm just going to go do those. Okay, let's get back to work. Color, let's make it like green. Okay, cool. These are going to be green. Wait a minute. Let me just delete these segments. I'm going to take this and I'm going to... Okay. Now we have a layer issue. Anyway, what I was thinking about was that do I like the lighter green or the darker green? I actually kind of like the lighter green, honestly. Yeah, lighter greens. It's brighter. Okay. We're definitely going to need to tone these down. Really where we copy from is really inessential, isn't it? And this has nothing to do with orangeness. It has to do... Right, okay. Okay. Perfect. I think this is good. I think maybe... And then what we'll do, we'll actually go thicker. And this, I think what we'll do is I'll delete these. Are these segments, do these matter for the construction? I don't think so. Okay, color. Let's go 50% opacity. Ooh, that's a lot. That's pretty heavy opacity, isn't it? Oh, and these are gray. I just noticed these. Oh. I'm trying to be at least consistent. It was this gray. Let's be consistent and say that it's solid. All right, there we go. Is there anything else we want to do? File. Oh God, I hope I didn't save over the other one. Oops. All right. I think this is good. Is there any like essential element of the reasoning I specifically want to highlight? I don't think so. Okay, so let's prepare it. How do we do this in i3? I don't remember. Oh shit, and I don't have window titles. Let me actually. How do I make all the windows have titles? There's a way to do this. Border. Yeah, we want normal. How about this? There we go. Oh, that's right. Different keyboard shortcuts than I'm used to. It's not going to be exactly the same, but ballpark. Ooh. I'm just going to title the video. I'm going to make it look like an N. Can I do that? Let's do this. I'm going to make it look like an N. And I'm going to say, and the video title is just going to be N. And it's just going to be this thumbnail with like no context. I like this idea. Okay. Maybe I should call it the N theorem. I don't know. Who knows? I like it. I like calling it the N theorem. And the last one was the V theorem. This is the N theorem. Okay, save file, export. Web page. 36. Upload. I want to make my own version of this website. But basically what I was thinking about, I want to make my own version of this guy's website because, you know, I don't know this guy. This website could go down at any point in time. It's a great website. You know what I need to do? I need to just email him and ask, hey, I really like your website. Can I make a clone of it and put it on my website? It's a really useful website. I've been using it in my videos. Do you mind if I make a clone of it and put it on my website? Where? Oh, right. Anyway, that's worth edit. No, I don't want it to. Advanced settings. I want it to be 700, 500. Edit the applet. I forget, like, I thought it was just ridiculous that it was asking that, like, I discovered that you guys can't, like, download the file and edit it, which was annoying. I didn't know that. I'm sorry. I thought that you would just have full access to it, but I guess that it's sort of maybe a closed source mindset, which I don't have. I have a very open source mindset, for better or for worse. Edit applet. I actually want to move this down and make it a little bit more centered. All right. 700. There we go. Done. All right. Oh, should I say Bitcoin is N? That would be an interesting title. All right. Profile. Let's see. Okay. See ya. Bye.